So in this lecture, we're going to look at the ideas around magnetic domains. So here's the question. In the previous lecture, we found that certain materials below a particular temperature magnetically order, they become ferromagnetic, they have a spontaneous magnetization. But you know from everyday experience that not all pieces of iron are permanent magnets. They are, however, ferromagnetic, but there's something about your average sample of iron that makes it not a permanent magnet. And the concept is, I think, familiar to you from prelims, but just to restate, here, for example, is my piece of ferromagnet. I've made it very pure. It is a single crystal, okay? And what we would find if we looked carefully is potentially something like this has arisen. Okay. So if we looked at all the atoms in this region of this domain, we would find their magnetization all pointed in this direction. But then if we looked in this region, they would point this way, and in this region, they would point this way, and in this region, they would point this way. Okay. So the magnetic field is contained within the sample. There is no, this material has no, doesn't create an external magnetic field. Okay. It's a cleaner version of that diagram. And the formation of domains is driven by a balance between various energetic terms. Okay. There's something called the magnetic energy, the magnetostatic energy. We have an anisotropy energy, an exchange energy, which we've spoken about before. And we'll see it's the magnetostatic energy that's mainly responsible for forming domains, while the anisotropy and exchange energies control the shape and the movement of domains. So the magnetostatic energy. This is the thing that's going to drive the formation of domains. It means that for a lump of iron, its ground state is not to be a permanent magnet. That's a higher energy state. The reason is fairly straightforward. In generating an external magnetic field here shown in blue, so this is a sample that is uniformly magnetized, this has an energy associated with this field. Okay. Put simply, it's able to do work. I mean, if I put a moving charge through here, work would be done on. We could do some work. Whereas if it splits into two domains like this, the field is much more contained. Okay, it doesn't spill out into space in the same way, so the energy is lower. And in fact, the lowest energy solution will be if the field is completely contained within the magnet. So most magnets, magnets left a long enough time will form themselves such that they form these multiple domains with no external magnetic field. Now this is a very simplified picture. There are ways of imaging what these domains look like. You can do it by, for example, putting some very small sized magnetic particles on a cut surface and look at how they become orientated. There are various transmission electron microscopy techniques. If you have some sort of spin polarized electrons, you can look at local magnetization and you can image domains in this way. They're often really quite complicated patterns that form, much more so than this simple one I've shown here. But the point is essentially the same, that they arrange themselves to have these kind of magnetic closed loops so that there's no external field outside of the magnet. Okay. So briefly about the anisotropy and the exchange energy. Now the magnetization in ferromagnets prefers to align in certain crystallographic directions. We call this the easy axis. So for something like BCC iron, the magnetization wants to be along 100. and the related symmetry related directions. Whereas it's a higher energy state to be magnetized along 111, and 110 is somewhere between the two. So that means that the material naturally wants to have the magnetic moments pointing along 100, and if you tilt them away from that, that costs some energy. Okay. So magnetocrystalline, sometimes referred to this as magnetocrystalline anisotropy. It's really quite small energy in many materials. In the transition metal magnets, it's actually really quite tiny. If you look at nickel, this actually reverses, and 111 is the easy axis in nickel, and 100 is the hard axis. It's not obvious to look at the crystal structure and predict it. You can do it with some ab initio calculations, some first principles DFT calculations. These are the sorts of things that Chris Patrick works on, but it's actually very small energies and really quite difficult to predict. So these are not obvious things to understand why. We just have to take it as an experimental observation that for iron there's an easy axis and a hard axis. The other term that drives spins is the exchange energy. We met it earlier. Okay, so the exchange energy wants spins to be aligned next to each other. Okay, so the question we have to resolve is what happens between domains. Okay, so in a domain we've got all our spins are nicely aligned, low energy, that's fine, but somehow the spins have to get from being aligned one way to aligned another way. So there are various ways in which we can produce a transition between domains. So we're going from a situation in which we've got all the spins parallel to each other in one domain, and then we need to go into the next domain and all the spins are parallel over here. Okay, there are various ways of doing that. What I'm showing here is the so-called block domain wall. There are various other types. You'll see, if you look online, you'll see Niel domain wall, so it's the spins can rotate in a slightly different way. So what we have here is everything is parallel. We enter the wall, and the spins rotate around until they're now pointing in an anti-parallel direction. Okay. And the width of this wall is controlled by the contribution from the exchange and the contribution from the anisotropy. So you might say, well, why couldn't we have a wall that was exactly like this? A nice sharp wall. Okay. From the point of view of the anisotropy energy, that would be perfect, because there could be essentially no anisotropy energy here, because these could be pointing along 100, and these could be pointing along -100. It's just in the opposite direction. So they don't have to point in the hard direction at all. They can just point directly in the easy direction. But that will have quite a large contribution from the exchange energy. Okay, so the anisotropy wants to have a nice sharp wall. The exchange energy would like to have it so that the spins rotated very slowly. So the difference between neighboring spins is only very small. Okay, and then we can add up lots of small things. So exchange favors a very large domain wall. Okay, now we need to be a bit more precise. Okay, we're going to begin by focusing on exchange. So the exchange energy, right? So, okay, so we saw earlier that this is equal to -2j S1 dot S2. And I can also write this as -2j S squared cos theta, okay, where theta is the angle between them. Now, we're going to imagine that the spins will rotate fairly slowly, so the angle between them will always be quite small. So for small theta, E will be -2j S squared 1 minus theta squared over 2. Okay, just using the Taylor expansion of this. In other words, the energy penalty of the spins being of an angle theta is just going to be j s squared theta squared. Okay, so that's the cost of being rotated through an angle theta. Now what we're imagining is we've got our domain wall. Okay, maybe this is the width of the wall, and there's going to be a rotation in total of pi. Okay, because we're going to go from being up to down. There should be, let's imagine there are n sites in the wall. So n atoms in the width of the wall. Okay. So what's going to happen if I look face on, I'm going to have my first one like this, my second one a little bit rotated. I'm going to exaggerate this, and we're going to rotate all the way around until we're aligned in the opposite direction. So if this takes n sites and we rotate pi in total, this means that the angle, our theta, will be pi over n. Okay. So the energy of our wall will be equal to the number of sites times j s squared. Now remember what theta is. Theta is pi over n. We need that squared. So this is going to be equal to j s squared pi squared over n. Now we need the energy per unit area of the wall really to make a good comparison. So we need the energy per unit area, and so we need to divide by 1 over a squared. So a is the where a is the spacing. Okay, because that will give us the number of such atoms per meter squared. Okay, so that gives us our final answer. Okay, which will be j s squared pi squared over n a squared. Okay, and that's a positive energy. So how could we lower this? Well, we could make n as big as we liked. So if it was just down to exchange, we would have a wall that just spans the whole magnetic sample. In fact, we wouldn't have any domains at all. Okay, that's just putting in the exchange energy. So now we need to move and look at the anisotropy. Now this is a little bit trickier. Okay, so anisotropy. It's also tricky for me to spell. We need a simple model. Okay, so the anisotropy is actually quite a complicated function of the angle between the spins, but we can make a simple model. So in a simple model, let's just have k and our anisotropy energy being equal to sine squared theta. Okay, so this will prefer theta equals 0 or pi. Okay, so this is saying to the spin as it rotates, the lowest energy state is if the angle is up or down. So you know, in iron that could be 1, 0, 0 or the opposite direction, and then the other direction costs energy. Now we might not have captured exactly how the energy varies. It won't vary just like cos squared theta, but this will do for initial model. So we would want to sum over all the atoms in the wall. So this would be this would be I is equal 1 to n of k sine squared theta I. Now, if we imagine the wall is pretty big, there's a lot of atoms, I can replace this sum with an integral. Okay, so to do that, I just need to make sure the average works out the same. Put that in, 0 to pi k sine squared theta d theta. Okay, if I do that integral, I will get nk over 2. Now I just have to be a little bit careful with the units of k. K is usually measured, is usually defined to be an energy density. So it's usually joules meters to the -3, for example. Okay, so in order to get the so the energy, I would need to do nk over 2 times a cubed, okay, and divide by 1 over a squared as I did before, and that will give me, so this will give me an energy in, so this is the energy per unit area of the wall. Okay, so this means that the wall energy per meter squared, sigma, is going to be the sum of the two contributions that I found. So it's going to be j s squared pi squared over na squared, which I found before, plus nk a over 2. And so we now see the two competing contributions. So the wall energy is decreased as I increase n, but the anisotropy contribution increases as I increase n. So what I need to look for is a minimum in the energy. So I need d sigma by dn, okay, and that's going to give me minus j s squared pi squared over n squared a squared plus k a over 2, and set that equal to 0 for a minimum. Okay, and that will tell me that n squared is equal to 2j s squared pi squared over k a3. And so finally, the my equilibrium value of n is equal to s pi square root of 2j over k a3. And the width of the wall will just equal n times a, okay, because that's the n is the number of sites, a is the space in between the sites. In other words, this is just going to be pi s square root of 2j over k a. Okay, so what we've seen is the anisotropy energy favors small walls. So just let me write up the formula I found before for the wall width. We had that this was pi s square root of 2j over k a. So the anisotropy favors small walls. This is k. The exchange energy, which was j, favors large walls. Yeah, so I increase j, I increase delta. And the wall width is always going to be a balance between these two competing terms. So just to give you an idea, typical measurement for BCC iron is about 500 atoms. So armed with this information about domain walls, we can think about how samples become magnetized. So here I've got, so let's imagine plotting B versus B0. Okay. So the applied field, so the internal field versus the applied field. And I'm going to find that I'm going to start initially with no applied field, no magnetization. Now, in that case, my material looks something like this. Here's my domain walls, exactly as I had before. Okay, all equally balanced out. Okay, and I'm going to magnetize my sample. What happens? So the internal field creeps up, and what I'm left with, what's happened in the material, is the domain that was aligned with the applied field has grown. So in this case, let's say it's this one here. So this domain is much bigger, and the other domains have got a lot smaller. So now this sample has a magnetization. Okay, and potentially, if I keep increasing the field, this will saturate, and I'm going to find that my material has become a single domain. Okay. So let's then look at what happens as I go around a complete cycle. So what we find is that the material, again, we magnetize it, and this value here is what we would call the saturation field. Okay, and then we take the field, the external field, we reduce it, and it doesn't go back to 0. It goes back to something like this. So the material is still a permanent magnet. Okay, we have to apply a field actually in the opposite direction of that value in order to make the magnetization back to 0. And we can actually then form a whole hysteresis loop like this. Okay. And the shape of this hysteresis loop is very much controlled by how easy it is to move the magnetic domains, how easy it is for those domain walls to move. Okay, so we can influence the magnetic properties of our material if we find ways to control how those domain walls move. So a very straightforward example is that in very pure iron, it's very easy to move the domain walls. So iron is very easy to magnetize, but it's not a very good permanent magnet because its coercivity, the field we'd need to apply to remove the magnetization is very low. So it's very easy to magnetize it, but once it forms a single domain, it's very easy for it to split again into lots of smaller domains. If we go for something like a steel, we've got a lot of different atoms in there, and those non-iron atoms make it difficult for the magnetic domain walls to move. So in order to magnetize the sample, we have to put a lot of work in. So it's hard to magnetize. But conversely, once we've magnetized, we've made something a permanent magnet, it's very difficult to remove the domain walls and demagnetize it. So a steel is typically a very hard magnet. Okay, so it's a good permanent magnet because it's very difficult to demagnetize.